Hello and welcome to Minerals, Rocks, and Fossil Talks. I'm your mineralogy teacher, Jen, and it's time for some Wordplay Wednesday. We're going to talk about conductivity. Conductivity refers to a material's ability to allow electricity or heat to flow through it. Metals tend to be very good conductors, and if you've never accidentally tried to grab a metal pan out of the oven without an oven mitt, you may have figured out quite quickly how conductive they are. Ouch. These metals' ability to conduct electricity or heat has to do with their outer shell of electrons and their ability to freely dissociate from the rest of the atom. Here I've got diagrams of 4 different metals, some common ones: zinc, copper, aluminum, and silver. And you'll notice that they have multiple shells of electrons. Those are each of those different lines. The outermost ones are the ones that are important. Those are our valence electrons. And those valence electrons are what are going to allow the transport of an electrical or thermal current. You'll notice that every one of these have less than 4 valence electrons in their outer shell. So if we look up at zinc here, we've got 1 and then 2 valence electrons. Copper only has 1 right there. Aluminum also only has 1. And silver only has 1. No, aluminum has 3. I can count. See? There's 2 and there is 3. Either way, they're all under 4. So this allows them to move more freely. They're not quite as connected to their atoms. Now here are 2 different diagrams. We have silicon and carbon. They have 4 valence electrons, which makes them semiconductors. Their valence electrons are a little more tightly bound to the atom, making them harder to move. Modifications to semiconductor crystal structures can allow them to conduct better, though. So silicon is a metalloid, so sometimes it acts like a metal and sometimes it acts like a non-metal. It couldn't make up its mind what it wanted to be. And then carbon, carbon is a non-metal, primarily a gas, but we can get it in non-crystalline and crystalline structures, namely coal and diamonds. Diamonds are really good conductors, and we'll get to that a little later. And then here, elements like oxygen and phosphorus, which are non-metals, they have more than 4 valence electrons. So oxygen has 1, 2, 3, 4, 5, 6, and phosphorus has 1, 2, 3, 4, 5. So more than 4. This binds them tightly to the atom and does not allow freedom of movement. We call these insulators. So, is it making sense so far? Excellent. I can't see you nodding or shaking your heads, but I'm assuming everyone's like, yeah, this makes sense. Now, to get an electrical current, electrons need somewhere to move to. Many simple experiments use copper and zinc because they are neighbors on the periodic table, with copper being slightly more electronegative than zinc. Zinc really, really wants copper's electrons. Electrons flow from negative to positive, while the electrical current flows from positive to negative. So, right here we can see that the current is flowing in the direction of these red arrows, whereas our electrons are flowing in the direction of these black arrows. Whee! Okay? Make sense? Great. All right, I told you the diamonds were coming back. Things change for nonmetals when it comes to heat conduction because it has less to do with valence electrons and more to do with the vibrations of the atomic lattice. This typically means that they conduct better at higher temperatures, unless they are high-quality crystals, like our diamonds. Diamonds are some of the best thermal conductors out there because of their highly ordered crystal structure. However, it is an electrical insulator. So it works really well for one type of conduction and not so great for the other. Now, heat moves in one of three ways: conduction, convection, or radiation. Conduction is the transfer of heat from a warmer material to a cooler one, such as grabbing the hot handle of a pot, which is going to then conduct heat into your hand and ouch! Convection is the movement of heat through a fluid, such as a liquid or a gas, as we can see with our water here. It's going to go in a sort of circular motion where heated water flows up and then cools down and sinks back to the bottom and keeps going. This is how we currently believe the mantle works with transporting magma. And then finally, radiation is heat energy transferred through electromagnetic waves. The sun is a very good example of radiation heat. It radiates the heat to the earth. We also get it off of the fire itself. You can feel heat radiating off of a campfire or things like that. Well, I hope you enjoyed learning about conduction and conductivity and all that fun stuff today in regards to heat and electricity. Tomorrow starts our new topic because it's May, and we're going to be talking about igneous rocks. So, tune in to learn about a famous igneous petrologist who revolutionized the study of igneous rocks. I will fossilize you later.